All right, let's talk about linear functions. Um, First, we need to become acquainted with slope. Slope is, as you probably know, rise over run. The rise or the difference in the y values is denoted with delta y. Now, delta y, whoops, not delta, delta y is one symbol. It's not two symbols, it's one symbol. It's a compound name that is made up by two items, delta and y. So it's not like, because if it were, if we had actually two symbols, then the deltas would cancel and we would be multiplying. And so, no, 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 it's just one symbol. Delta y is one symbol, not two. So, not two. So just be aware of that. It's one symbol. It never ever splits or anything like that. It's just one thing. It's just a long variable name. Um, yeah, that's what it is. So delta y is how much the output changes, and the delta x is how much the input x changes. One question I ask my students is, let's say somebody tells you that your income, your year, oh, I already gave that up. But pretend your income is going to go up. If somebody says your income is going to go up by $3, okay? So again, somebody says your income goes up by $3. Is that good or bad? Okay, so period, is that good or bad? Question mark. So, well, it depends. If it goes up by $3 per year, well, if you're making, I don't know, $10,000 a year and it goes up by $3 a year, if that is a raise in your income, that's almost like an insult. It's like $3 in a year. If it's $3 a month, well, still not very good. $3 a week, well, that doesn't even pay any of, I mean, a little bit of the taxes. $3 a day, okay, that's a little better. Maybe half a lunch. You can buy half a lunch or something like that um, in a fast food place. Three $3 an hour. Well, that's a big difference. That makes a huge difference for many of us. So saying that something goes up or down by any amount, you know, it's is meaninless unless we have a time period of reference. Yeah. So so that's why we need to have a quotient, and they also call the rate of change. Rate of change, same thing. So because if somebody tells you your income is going to go up by $3, over what period of time? If it's per hour, great. If it's per year, that's really bad. I mean, that's hardly anything. Uh, I'm assuming we are making somewhere in the neighborhood of, let's say, $10,000 a year or something like that. You know, $3 is not too much. Um, um, so, so just the output, the change in the output, um, is not important. What is important is the ratio over what period of time. That's what makes this very important, and that's why we have to have two values. Now, oftentimes, though, the rate of change is given as a one number. So in that case, it is understood what the denominator is. Yeah, so when slope is given as a single number, comma, then it is understood the denominator is 1 unit. Now, somebody could say, well, see, and it gets a little tricky because somebody could say, well, 3 is really 3 over 1. And somebody could argue, well, 1 what? 1 what? 1 year? week, hour. I mean, you can go on day. What is it? Month. Um, it's so it is implicit that there is a set of units already involved in this picture. Um, yeah, yeah. So it could be that in the conversation we are talking about um, the rate or the salary of in dollars per hour, then that would reference this to an hour. Yeah. So sometimes the context tells us the units, but if there's no context at all and just the number is thrown to us like that, then we don't know. We don't know. Somebody has to clarify. So it's a little tricky because in this context, when we write the slope, so yeah, the slope as 3/3, which is the same thing as 3/1, technically speaking, it is understood what the 1 means. All right. So the slope tells us how fast something increases, because a steep slope, so let's say your salary goes up by $3 an hour, every year. So let's say we're making 7.50 per hour in 1 year. So the next year we would be making $10.50, and the next year we would be making $13.50 per hour, and so forth. So that increases very quickly. I mean, by the time we are here, then that is almost double this. That is getting close to double that. And then the next year, 16. So that's more than double. So this is a very steep slope. 3 in this context is very, very steep. Yeah. So that is very steep. If, on the other hand, so this is a slope. Oftentimes we use m for slope, a slope of 3. Say you start out with this, but your slope is 1/4. That means that it takes 4 years to go up $1. So that means that after 1 year, we would be making $7.75 per hour, and the next year $7.50 per hour, and the next year, oh no, that doesn't make sense. That goes back down. So that would be 8, not 7.50. Yeah, $8 an hour, and then 8.25, and so forth. So this is a much reduced slope, 1/4. But then it depends on the amount of money we start out with. So this is sort of a starting job, and then it can go up slowly, or it can go up fastly, or um, let's say a dentist or somebody like that, who makes much more. Say we have a plumber, or somebody who has a particular good, a skill, a mechanic, plumber, an electrician, somebody like that would make, I'm guessing, at least $30 an hour at the very least. They should, because they're very specialized. So then the $3 would be at 10%. That's not too bad. That is still quite fast though. But the 25 cents would be very, very small in comparing to here. Yeah. I mean, if inflation is about 1% per year, you would expect, oh, 30 cents here, 1%, 10% is $3, so 1% is 30 cents. Yeah. So what I'm trying to say is that the slope is not necessarily attached to the output. So let's put a slope of, again, 1/4. So after 1 year, instead of making $30 an hour, we could be making $30.25 or $30.50, and so forth. So the slope doesn't have much to do with the output itself. You can have the same slope as in those two cases, the same slope, but here it means less, because adding 25 cents per year is not as significant. It is much smaller of a percentage than here. Yeah. So that is what we mean by slope. And this, when we draw the slope, 3, so 3 per horizontal unit would mean So 1 unit to the right, and then 1, 2, 3. That would be a slope of 3. That's about how a slope of 3 looks like. A slope of 2 would be 1 over and 2 up. So that is a slope of 2. A slope of 1, and practice this. A lot of students, a lot of people neglect to think of this, and it is very handy to actually have an idea what slopes look like. So slope of 3, slope of 2, slope of 1. Slope of 1/2 would be 1 over and only half up. So that would be a slope. And it isn't that this is shorter, because you can always extend it longer. The way this in, slopes, the way this inclinates is different. So 1, 2, 3. The farther we go, the less of a difference in the angle it looks. At the beginning, the angle changes quickly, and then as we go higher and higher, the angle changes less. So this is a slope of 1/2. A slope of 0 would be a horizontal, so it doesn't go up or down. A slope of -1, so the rise is negative, so we go down. If this is 1 unit and this is 1 unit, that is the slope of -1. So notice that how this is very different than that. And remember, I have mentioned this in a previous video. Remember, we read slopes from left to right. So the way we do it is take a pencil, anything that is vertical, and slide it to the right in order to keep up with the line. If the pen is going down or the other instrument is going down, then that means we have a negative slope. If on the other hand, when you move the pencil from left to right, the pen has to go up to keep up with the line, that means we have a positive slope. So we have negative slopes and positive slopes. Okay, I just wanted to check that I was actually recording. A few days ago, I recorded a video without pressing the recording button, and so I was just talking to nobody for half an hour. It's funny after the fact, but in the meantime, it was kind of frustrating. All right, so the typical function, there's two ways to write actually many ways to write the function, but the one we're going to use a lot is what is called a slope intercept form. So mx plus b will be our slope intercept form of the equation of the line. This is written as a function. We can also write it as y equals mx plus b. So this is the slope. That m represents the slope. And this b is the number used in the y-intercept. So it's the number corresponding number I'm missing an n, corresponding to y-intercept. So the y-intercept is 0b. So be aware that the y-intercept point will have two coordinates, not one coordinate, but two coordinates. All right. Now, the least amount of information we need to obtain a slope is 2 points. You need to have 2 points, a starting point and an ending point. So we need 2 points to find a slope. All right, so let's look at some examples. Let's say you have the point 3, 7 and the other point, let's go farther to the right, 5, 12. Okay. So 3, 7 is somewhere. And then we go from 3 to 5, 2 units to the right. So let's pretend that's 2 units. And then from 7 to 12, we go 5 units up. 1, 2, 3, 4. So that sorry that the picture is kind of bumping into this line, but then we will have 5, 12. Now it doesn't matter what the output is, which is 7. What matters is how much the output changed in between those 2 points. In fact, I'm going to, while I'm doing this, I'm going to do a second example, and we're going to have 3 comma 5,981 comma, I mean, that's 1 point. So the input is 3, the output is 5,981. And the other point is going to be 5 comma 5,986. Okay, so I don't need to have an, I don't have to have the x-axis. I can just draw the initial point, which is 3 comma 5,981. And to get from this point to this point, we gotta go 2 units to the right, 1, 2, and then from 5,981 to 5,986, there's 5 units, 1, 2, 3, 4, 5. So notice that the picture from this point to this point is the same picture as from this point to this point. It is exactly the same, 5 units up and 2 units forward, which means that the slope is the same. See, the slope here is going to be how much we went up, and that would be delta y, and we went up by 5 units, whoops. And how much we went forward, which is called delta x, is going to be 2 units. And the slope, sorry to put it too close to this, the slope is the rise, which is the delta y, over run. And if this doesn't simplify, we just leave it alone. That is the slope. Here, even though this is way sky high, 5,981 is a huge, gigantic output. The slope is still, from this point to this point, 5 units. Delta y is 5 units. This guy is still 2 units. And so the slope is 5 over 2. That's an equal sign there. So the slope measures how much we change. The slope does not measure the output itself. It only tells us how much something is changing. Again, it doesn't tell us the output. Yeah. So one example I give in my classes is when I'm talking about slope is the domestic gross product. The United States makes millions and millions and millions of things. The domestic gross product measures the goods and services the United States produces. So the United States makes cars and agricultural items like corn, rice, beans, tomatoes, planes, so there's a lot of things that are produced in the United States, tons of things, lots and lots of things. Furniture, and also the services. This measures the services. When somebody goes and gets a haircut, that's also something that we are producing. So that's a service. When somebody gives a ride, that's a service. I mean, with a taxi or something like that. A bus driver who's driving the bus is providing a service. So that contributes to the domestic gross product. And the example I give is if the domestic gross product has a slope, and this is a hypothetical, has a slope of 0, is that a bad thing? 0%, so it does not increase. And my reply to my own question of whether 0 is a bad thing or not is, well, it depends. If it's not for too long, I don't think, this is my personal opinion, I don't think it's a big deal. because we're still producing many things. So I have to check, but I'm going to guess it's in the billions and billions of dollars of production in the United States. So if one year that production does not increase within reason, again, within reason, if the slope is zero, that just means that we're still producing the same amount as the previous year, which could be a lot. So if one year, for instance, our production went up by a lot, and then the next year the production stays stable, that means we don't produce more. That's not necessarily a bad thing. That just means we are doing really well, and there's no need to grow, perhaps. Okay. And again, I'm not an economist. I'm not an expert. I'm just telling you my thinking when the slope is equal to zero. I'm telling you that, or trying to tell you, that a slope of zero does not measure the output. It only measures how much the output increases. If the output is really, really good, hey, that's not necessarily a bad, and it doesn't grow, that's not necessarily a bad thing. If the output is bad, I mean, it's low, then you do want to have some growth in the output. So be aware of the output. And versus the slope, they are not the same thing. Okay, I'm going to use this example to come up with the equation for the function, the line function that joins those 2 points. So I'm going to use the same points, 3, 7, and 5, 12. And we want to actually we want to find the function that connects, the line function that connects those two. So we want to find the line function that connects 3, 7, and 5, 12. There's many ways to ask this question or come up with this problem. Another way to ask this is to find the equation of the line between or through those 2 points. Same as finding equation of line through 3, 7, and 5, 12. Okay. So we have some information already about this. Y, or f of x, is equal to 5/2 x. How do I know it's 5/2? Because that was example 1, and we use the same numbers. So we already found the slope. This tells us that every unit, and by the way, there's a couple, let me back up a little bit here and talk more about slope. As we do this problem, let me say more about slope. Okay, so if I say I'm going to sell you, this is just a silly example, pencils, and I'm going to sell you 5 for $2. So 5 pencils for $2. And then next to it, let's say I have a store and there's a bunch of pencils in a basket, and I put a sign, 5 pencils for $2, or 10 pencils for $4, or 25 pencils, there you go, for $10. Which is the better deal? 5 pencils for $2, 10 pencils for $4, 25 pencils. Wait. 5 pencils for $2. Which one is the best deal? You who are watching the video, which one is the best deal? 5 pencils for $2. Well, the first two are the same, because double this, double that, and it's the same thing. So you get the double of pencils, but you gotta pay double the amount, so it's the same per pencil. How about the 25 for $10? Well, if you multiply by 5 and multiply by 5, yep, it's the same. So they're all the same. It's a gimmick. If I put this in a store, in a sign, in a basket with a bunch of pencils, they're all the same. It doesn't make any difference. I think I've seen this in this, not exactly this, but in some places, things where it doesn't it doesn't make any difference whether you're buying two or three. It's the same as if you were just buying one of something. Or there's many ways to write this. So how much is each one? Is it 40 cents or one pencil for 0.4 or 0.440? Yeah. So 80, yep, that's the same thing. So we can put any of those. We always put the simplest one. It's sort of illegal to put anything that is not the simplest way of representing a number. And there are essentially two ways. We're going to prefer the fraction. Decimal will be okay as long as we don't have an infinite decimal. If we have an infinite decimal, avoid that. Then you have to really put the fraction in my classes. But so we can do this or that. Yeah. What we cannot put down is 25 over 10. I mean, we can start with that, but then we have to simplify that fraction. Anyhow, we still need to find another number, because all this does is it tells us the slope, but it doesn't tell us the output. When we're putting together a function, we have to have both the slope and a way to measure where we start with the output. The slope doesn't tell us the output, as I was trying to tell you here, with these two examples. The output is gigantic, the output is not so much, yet the slopes are the same. Okay, so the slope doesn't tell you much about the output, which means if we want to have a complete picture, we have to have the slope and something that tells us something about the output, a number that tells us something about the output. So, okay, so we go 2.5. Now, let me start this with a very simplistic way of obtaining the answer of what goes in here. So we want to have a number here. What is that number? Okay, so I'm going to do this with a picture. And some students, some people, when they see me trying to explain this, they say, well, there's an easier way to do it. Yes, I know there's an easier way to do it. I'm showing this not to show you the easiest way. I just want us to understand what's going on. So please bear with me when I do this. So 3, 7, that's not necessarily a good point. Let me start over. I'm just going to put a point here. 3, 7. And then we go 2 over, 1, 2. And then to get to 5, and then 5 up. 1, 2, 3. I apologize for not thinking too far ahead. So again, 3, 7. 1, 2. And then 1, 2, 3, 4, 5. And then we are at 512. And we have this line. Okay, so that means that, so this is this delta y for the corresponding to delta x, which is 2 units, is 5. And then when we divide, we get 5 halves, which is 2.5. 2.5 is the same thing as how much it goes up per unit. So per unit, we're going 2.5 up. So this point in the middle would have to be 4 and 2.5 more than 7. 4, 9.5. I'm going to keep fractions. Okay, so again, this is not the easiest way to come up with this number, but I'm doing that on purpose so that we understand what's going on a little better. If we already didn't already. So if we go 2 units to the left and we follow this pattern, we're going to be, I was going to go only 1 unit, but I want to get to 0. That's where I want to start. Where does the output start when the input is 0? So I'm going back to 1, and using this pattern of going up by 5 every 2 units that we go across. If we go across 2 units to the left, that means that we have to drop 5 units. So that means that this point has to be 1, because 2 are to the left, and then from 7 drop 5 units down to 2. Okay, and then I want to keep going to the left, and eventually we're going to cross the y-axis, which is the starting point. That's when x is 0. Okay, so I want to know what this point is, and it's not 2 units to the left because this is only 1 unit to the left as opposed to 2. Okay, so 1 unit to the left means only half the drop as I'm going to the left. And as we noticed, we were going down by 2.5 per unit. So if we go down, this point is going to be 0, comma, 2.5 units lower. Okay, so this is 2, and then we go down 2.5 units, we're going to be a negative 1/2 unit. So that means this is the very starting point, and by start is a relative term. Where do you start? Well, where do I start what? When do I start my adulthood? That's when I was 18. When do I start my life? Well, I guess when I was born. And when do I start, I don't know, working? Well, that's when I got my first job. Start of what? What we mean by start is when the input is 0. So that's the starting point. And we also label this as the y-intercept, but keep in mind that that's when the input is equal to 0. So -1/2. That is the function. And again, this is not the easiest way to come up with this, but I think it's a very, very good way to actually get your hands dirty and think, okay, I see what is going on. I see where we're going. I see why we're getting the negative, okay? Now, you can find in many places where, how to come up with the other number. So let's go over that real quick. If we know that the output is equal to 5/2 x plus a number, and we don't know what this number is, now we do. But if we didn't know that, well, the line has to go through this point, 3, 7. So what we can do is pretend this is 7, which is the output, and pretend that this is 3, corresponding to the input of 3, 5/2 times 3 plus b, and then solve the equation for b. So, okay, we're going to multiply 5 times 3, so that's going to give us 15/2 plus b. And then anticipating we're going to subtract 15/2 from both sides of the equation, we convert this into halves. So 7 is the same thing as 14/2 halves because we can multiply by 2 and divide by 2. And then we can subtract 14/2 minus 15/2. So b will be -1/2, which is that. But this is the algebra. Now, don't take me wrong. There's nothing wrong with doing this in the sense that if we want to find b, yes, that's a pretty fast way to get it. What I would like to add is that watching where the -1/2 comes from is valuable. It adds to our understanding of why we get the -1/2. This is a little bit of a blind way to obtain the solution. I mean, we trust that it's going to work, but here I can actually see what is going on. Yeah. Yep. Yep. By the way, let's move on to add more to this. So we did have y equals 5/2 x plus question mark. If we were going to use 5/12 instead, because we did use, what did we use? We use 3/7. But if we wanted to use the other point, 5/12, we could. 12 equals 5 over 2 times 5 plus b. So pretend there is a number b and draw what it is based on given information. So again, anticipating we're going to subtract halves, I'm going to change this into 24 halves. 12 is the same thing as 24 halves. And that is 25 halves plus b. So when we subtract 25 halves from 24, sure enough, b equals -1/2. So we end up with the same answer. There it is, regardless of whether we use one point versus the other. That is true. Yeah, that is just true. That is just the way it is. It doesn't matter which one we pick. Yeah. Let's talk about parallel lines and redefine what parallel means. Parallel lines means lines with exactly same slope. Same slope. That's it. Same, if they have the same slope, or if they have the same absence of slope, then we have parallel lines. The vertical lines don't have a slope, by the way. So if two lines don't have a slope, that means they're parallel. If one of them has a slope, and we claim that the lines are parallel, then they have to have exactly, identically the same slope. If one is off by a little bit, then they're not parallel. So as an example, 4, yeah, that's 4. Okay. Y equals 5x plus 3,978.2 versus y equals, so those are two lines, 5x minus 3. Are they parallel? All you have to look is the slopes are the same. So yes, they're parallel. Yes, they are parallel. Yep. If somebody asks you they're parallel, yeah, you can see it. Same slope. That is exactly what I'm trying to show here. Parallel lines means exactly same slope. So if one is off a little bit, so example 5, if one is 5.00001x plus 3 and versus 5.0001234 x plus 3. Are those two lines parallel? If you were to graph those on a graphing calculator, I dare to you to find that they are not. They would look very, very much the same, almost the same, one on top of the other. Now that would be if you are in a small window. I bet if you change the window enough, you can probably start seeing that one is actually steeper than the other. This one is steeper than the first one. Are they parallel? The answer is absolutely not. So these lines are not parallel. Why not? Well, because the slopes are not exactly and identically the same. They're close, but in mathematics, something is or isn't. We have to be very strict about that. In very, very pure mathematics, something is or isn't. We can speak about being close, but if we are asking, are they or they're not parallel, we have to say, no, they're not, because this is steeper than that one. They're going to diverge. Eventually, if we go far out enough, they're going to be getting farther and farther away from each other. So no, they're not parallel. One thing I wanted to mention is that in math, we allow things to be compared to themselves. Okay, so, when we are talking about everyday conversations, um, we can ask questions about comparing, who's taller, Jim or John? And then you say, oh, well, Jim is, I don't know, 6'2", and John is 6'3", so one is taller than the other, and yeah. But we never ask ourselves who's taller, John or John, or, when we're speaking about exactly the same person, or we never say, well, John is the same height as John. It's kind of weird to say that. So yeah. So if I say Tom is as tall as Tom, and we mean the same person, that is really weird to say. Nobody that's who says that? We always have comparing two different people. Tom is as tall as Sally or somebody like that. But comparing things to themselves is weird in everyday conversation. In math, that's done all the time. We always do it. It's not a problem. So that's kind of like saying, is 3 equal to 3? No problem. Sure, it is. That is true. Yeah, it is. So the reason why I'm bringing that up is because in math, it's okay to ask this question: is y equals 5x plus 3 parallel to itself? Which is something that we wouldn't dare to ask in an everyday conversation. And the answer is yes, they are. I mean, yes, it is parallel to itself. So be aware that in math, we do include things that in everyday conversation would be weird, such as things comparing them to themselves. Yeah, yeah. So that is why I'm bringing that up, because we can we can uh, we can say that this is parallel to itself with no problems. That doesn't bring any contradiction. Yeah. Otherwise, if we don't allow that, and that is more of a convenience than anything else, if we don't do that, then we will have to add more to our propositions. We will have to say, well, except when they're not the same. And instead of that, we just include it, and that way we save a lot of time and effort and energy and thinking. It's a little twisted to do that, but it's okay with us. Yeah. When are things perpendicular? Perpendicular. So two lines are perpendicular if the angle in between is 90 degrees. It doesn't matter which direction. Well, but so right now, pretend that is 90 degrees. So if we turn one, then the other one has to turn along with that. So that is the 90 degree. So perpendicular means 90 degree. So can a line be perpendicular to itself? No. I mean, we are allowed to ask the question. That is not a problem. We can ask the question. And the answer is no. No, because they have to be different. They have to come out at different angles. Now, a rule which is true is that two lines are, and the symbol for perpendicular is a T upside down. So two lines are perpendicular if their product is, no. Yeah, that didn't make sense, because what do I mean by multiplying a line with another line? Two lines are perpendicular if, sorry to do this, if the slopes, actually, if the product of their slopes is -1. So we are judging, we are making the statement of whether two lines are perpendicular or not, or parallel or not, based on their slopes. Yeah. There is one exception to this. This is not complete. Because what if one line doesn't have a slope? Then we cannot speak about the product of a slope with something else. So, okay, so two lines are perpendicular if the product of their slopes is -1, comma, or, so there's an or, if one is, sorry to do this, horizontal, while the other is vertical. So there's a big or in there. This, if they have a slope, then they are, and if the product of the slopes is -1, then they are perpendicular. But there's another case in which they could be perpendicular. If one is horizontal and the other one is vertical, which makes sense, one is horizontal, the other one is vertical, then the lines are perpendicular. So let me just keep track of the example numbers. So last example was 5. So example 6, okay, y equals 1/3 x plus 7, y equals versus 3x plus 13. This number does not matter for purposes of judging whether we have perpendicular slopes or not. That's an abuse of language. Perpendicular slopes. Well, I guess that sort of makes sense. But what I mean to say is, if the lines are perpendicular, do they multiply out to -1? You know, what is 1/3 times 3? Okay, so note 1/3 times 3 equals 1. So the answer is no, they're not perpendicular because that's not -1. So no, they are not perpendicular. So remember, that's the symbol for perpendicular, a T upside down. If we wanted to change one of the two to make them perpendicular, sure. So this is a follow-up of 6. 6, continue. I mean, not like we have to fix it, but if we wanted to fix it, if we had -1/3 x plus 7 and keep the other one as is, then we're good if we want them to be perpendicular. So those two are perpendicular. Or you can put the negative on here. One of them has to be negative, otherwise we wouldn't be able to obtain a negative product. So that would fix if we were asked to fix. Oftentimes we're not going to be asked to fix anything. We're just going to say, no, they're not perpendicular. And there's no such thing in this kind of definition as close to perpendicular. I mean, there is, but if we ask a strict question, are those two lines perpendicular? The answer is not. So if this was one, okay, here's a good, this is what I'm trying to say. Let's say y equals 0.33x plus 7 and versus another line that is going to be -3x plus 11. This is a good problem. I can see myself writing that problem as a test question. So the question is, are those two lines perpendicular or not? That's a good test question. Somebody could say, wait, well, that's like a third, and this is 3. So when we multiply a 3 times a third, we get 1, and this is negative, so we get -1. So yeah, nope, that would be wrong. That would be false. They're close, but we're not asking whether they're close. We're asking whether they are perpendicular or not. So, okay, so -3 times 0.33 is not -1. It is -0.99. It is close to -1, but it's not equal to -1. And in mathematics, that is a big deal, a huge, gigantic deal. They're not equal. Not equal. So consequently, those two are not perpendicular. Thus, the given lines are not perpendicular. Yeah, they're close to being perpendicular, but so if you draw one is going to have a negative slope of 3, the other one is going to be really close. To the naked eye, they may look perpendicular, but that's why we have algebra, so that our eyes can see something, but then we can tell in reality that there is something else going on. That, yeah. If somebody says, I want you to build a line, 8. Okay, so build a line, and by that we mean an equation of a line. Okay, so build a line, and I want it to have certain properties. I really like this line, with same slope as y equals 5x minus 17, and through 4, 3. Okay, so build a line with this characteristics. I really like this line, but I don't want it to be exactly this one. I want it to go through this point. Okay, so put together a line, build one, make one with this. Oh, I usually we don't ask that question, but let's answer the question anyway. So the same slope as this guy, but passing through here. So all we have to do is borrow this slope or copy it down. It's like if somebody says, I really like that car, the color in that car. And so somebody has a color in a car that is really, really cool. Something like a violet, a green, or I don't know, or an orange, a really cool color. And then you tell a place where they paint cars. I really want this color, but not in that car. I want it in this other car. I don't think anybody paints cars anymore. They used to paint them. But anyway, so you borrow the paint color, and then you just use a different car to do that. Maybe that was a very bad analogy. Anyhow, so borrow the 5. So that is the end of the problem. And to put it together, borrow the 5, put the 5 here, and then figure out the b value that causes this line to go through this point. And we know how to handle that. The slope is 5. In fact, I'm going to do it the really, really long way. And there is merit to do that, by the way, because we understand better what's going on. When the input is 4, let's do this with a table. When the input is 4, the output is 3. The slope is 5. So when we go up by 1, the output goes up by 1 as well. No. It goes up by 5 because that is the slope. So the output should be 8. When this goes up by 1, this goes up by 5. That is how much. Remember the $3 or the 25 cents? That's the slope, how much we go up per year. So this is telling us how much we go up per unit. Every increment in unit goes up by 5. So let me squeeze a 6 in here. If we have a 6 in the input and we went up by 1, that means that the output has to go up by 5 because that is the slope. So we would be at 13. Okay. So let's back up. How about at 3? Well, we would have to be at -2 because we go up by 5. So the 5 has to be consistent. How about at 2? Well, we will have to be at -7 because when we go up by 5, we end up with -2. How about 1? -12. How about 0? -17. Bingo, bingo. That is our B. So the equation is y equals 5x minus 17. That will do. I know, guys, many students, when I show this, tell me, Mr. Saldivar, that was the hardest way to get the answer. I agree. This is not the fastest, easiest way to get it. But now we have a better grasp of what the 17 has anything to do with the outputs and the inputs. The input is 0, the output is -17. That's our starting point and our mark, ground 0. And as we move forward, 5 by 5, because that is the slope, eventually we get to 4, 3. And we have to start out so far down, -17, so that when we get to 4, because the slope is so high, so big, so we have to start that low so that when we get to 4, um, we made it above 0 and we end up with 3. Yeah, yeah. Having a better understanding of what's going on also helps us detect mistakes. So there's two reasons why. One is we have a more conceptual understanding of what's going on when we do this the long way. And I'm not saying to do every problem the long way. Once in a while, get your hands dirty and actually try to figure this out without a formula. Um, yeah, sometimes formulas are good, sometimes formulas are not so good. I think a mix of the two is the best. Occasionally, don't use a formula and try to figure it out by common sense, by just thinking about a problem. Um, Speaking of formulas, I did not give a formula for the slope. Okay. The formula for the slope is, whoops, not y. M, the slope, is y2 minus y1 over x2 minus x1. And again, that is a formula. A lot of students know how to use it, and it makes sense to them. And by the way, coincidentally, it is the same thing as, and every time it will be the same as a y1 minus y2 over x1 minus x2. As long as we're consistent, and by the way, we're assuming that we have x1, y1, and x2, y2. As long as we're consistent and we go, if we subtract y2 minus y1 on the numerator, and we're consistent and we do x2 minus x1, we're good. Or if you do y1 minus y2 in the numerator, then we have to go x1 minus x2 in the denominator. As long as we're consistent, we're good. The problem is if we do y2 minus y1 and then x1 minus x2, because then we're not keeping the consistency. Yeah. So again, this is one of those things that it's good to know the formula, but it is also good to know, like here in this example, one of the first ones. Yeah. When we were looking at the slope, I didn't use a formula. I just went and looked, oh, 3,7 is there. And I eyeball it 512. Notice that I'm just using some marks. I'm not using a ruler to very, very neatly write the units. And I can tell, okay, so from 7 to 12, which are the outputs, I get 5. And then when you look at the inputs, going forward, then we get 2, from 3 to 5. So I'm using a little bit of common sense. 3, how far is 5 from, if you start out at 3? Well, it's 2 units. Yeah. As opposed to using, I could have just said, oh, 12 minus 7 is 5, 5 minus 3 is 2. There's the answer, 5 over 2. Yeah, sure. But then we have we don't have as deep of an understanding if actually we do this without the formula. I'm not claiming the formula is bad. The formula is good. I'm just saying once in a while, don't use the formula so that we can recoup our understanding of what's going on. There's another reason. There's two reasons why it is good sometimes not to use a formula, because then we grasp an understanding of what's going on. So if somebody gives an answer that is incorrect by mistake, then you can detect, hey, that doesn't make sense. So for instance, let's say, I'm looking for the example. Yeah, let's say I make a mistake in my computation. By the way, we did not use algebra to find this b. We just used a table. Let's say I use algebra and I make a silly computation error, and I put plus 17 here instead. Okay. Wait a minute. I'm just looking at this. Build an equation. Don't tell me that this is, I just realized this is a 17 and so is this, and they're both negative. Let me just make sure. Yeah. This is so weird. It's very unlikely that I take a point at random, and I truly just pick that point at random, and actually matches the problem that we already had. I just noticed that this 17 is exactly the same as that 17, and typically that is not the case. Yeah, that was a pure, that's kind of creepy that I picked 4,3 at random in my mind, and that actually matches this. That was totally unintentional. Yeah. So the answer is the same as the problem. It's kind of like telling somebody, well, I want you to build me a piece of furniture that has certain characteristics, and that piece of furniture already exists somewhere. You can just buy it instead of having custom made. Anyway, that was just purely coincidental. So if you need a line that is parallel to another line, borrow the slope. That's what I was trying to do in this, show you in this problem. So if somebody says find, build an equation that is parallel to another equation, just borrow the slope and put it in here and then find the b. It is totally creepy that we have the same number. That was unintentional and probably a little confusing too. Anyway, this is it for this section, or for this review of this video rather. And we're going to stop the video here.